All right. So I want to just spend a few minutes. I don't want to spend the whole period or even more than 5 minutes on grades because I do have a lot to cover today. But I want to talk a little bit about grades in the class. Some of you have been sending me emails about grades. So um, my guess is that because of the pandemic, the grades, this is probably true university-wide, the grades are lower, probably have been when people were actually in class. For example, when I taught this class last time, it seems like the average grade um, this time is about 10 to 15 points lower than it was the last time I taught this. And the last time I taught it was in class. So what I'm going to do, and this is something that's tentative right now because um, I want to make sure that all of you do your best when you take this class, especially from this point forward, is that I will come up with a grading scheme where your grades will probably end up being better than what you think, even better than what's in the syllabus. Okay. I'm not going to go through it right now with you, but just know that even people who are getting, some people, not all, but some people getting below 50 um, on overall grade right now, it's possible they will get, they will not fail. I'm not saying they will or won't, but there's a possibility of that. Um, So just know that that is there as a possibility that I might do that. And the only reason I'm saying it's a possibility is because I want to make sure that all of you do your best from this point forward, and then you're not going to say, all right, Professor Barish is going to curve everything, therefore I don't need to work, and he's going to curve it anyway. And my response to that is if I see evidence of people purposely not working, not or getting very low grades, then I'm going to go back to the original grading scheme in the syllabus. All right. So again, I don't want people to do that. I don't want people to collude and decide let's just not do well because that why work hard if you're going to not you're going to get the same grade anyway. But that's not true. I want you to work very hard on this course, the best that you can, and do the best that you can. But just know that this alternative grading scheme is a strong possibility as long as I see evidence that you're all working. All right. And remember that after the end of the semester, if you're not satisfied with your grade, you can always take a pass or no credit as an option. That's something you can do later. I believe it's still available to you this semester. So in some ways, it's not. I know some people have withdrawn from the course, just a couple, but they did it because they don't have time for it and they decided to withdraw. That was their decision to do that. At this point, given that you have this pass no credit option, it makes sense that you should probably just go right through and do the best that you can. But again, if I do this alternative grading scheme, your grade will probably be better, maybe even one grade higher than what you may think, given the grading scheme in the syllabus. So just make sure that you do the best you can from now on. Now, what's left in the course? There is there's going to be a quiz this week on chapters 8 and 9. That will be on Wednesday. All right, I've already created this quiz, so it's ready to go. And it's basically concepts and short calculation type of thing. So make sure that you review chapters 8 and 9 before you take the quiz. There's also homework, which I'm in the middle of developing, which also covers chapters 8 and 9. I'm about halfway there, and I should have it completed by our next class, and then I'll post it, and it'll be due probably by Sunday or Monday of next week. For chapter 10, which is on hypothesis testing, there will be a separate quiz on that, which will be on the day of the review for the third test. That I believe that is 2 weeks from today. Would be the day of the review for test number 3. Test number 3 would be 2 weeks from Wednesday. All right. So basically, we have this week and next week as far as learning new material. I would highly recommend that you attend class through the next 2 weeks for sure. Should be attending class anyway, but that that will be it for new material. And then the week after that, 2 weeks from today, is when we'll have a review and then take test number 3. So there are 2 more quizzes left. There are 2 more homeworks left. There'll be a homework also in chapter 10, which I will post, create that and post it. And that'll be it for as far as everything before the final exam. Okay. Final exam is on Monday, May the 3rd. I believe it's 12:30 to 2:30. I have to double check that, but I believe that's what it is. It's always 2 hours. If for some reason there's a conflict, all right, with another course that you're taking, if there is a conflict, you have to let me know soon, by the end of next week. All right, you have to let me know. You can't just say, tell me the day of the exam, the day of test number 3, or the weekend before the final exam. No, you can't do that, because you'll be taking this final exam early, not late. All right. I won't accept any late exams. Now, if there's an emergency, there's COVID and all sorts of emergencies that could happen, you have to obviously notify me for the 3rd test and for the final exam. If you're passing the course, if I see that you're passing the course, then I will enter an incomplete for you. Incomplete. I think you have to ask the university if it's a medical incomplete, and then the university will notify me, but it'll be an incomplete. If you're failing the course, which most of you will not be, but if you are failing the course, you cannot get an incomplete. That's just the way it works for all courses. All right, so that is pretty much what I wanted to say. Also, I adjusted test number 2. Came to my attention that a couple problems on test number 2, there was some, I would say, ambiguity on the way it was graded. And I decided to give everyone credit for these problems. So I believe these are problems number 8 and numbers 15 through 17. Now, if you already got the 8 questions correct for those problems, you don't get any extra points for that. But for those of you who got questions wrong, number 8 and 15 to 17, no matter what they are, whatever you answered, you got credit for. So everybody will get credit for all those questions. Again, if you got it right, there's no extra credit, no credit you'll be given for that. If you got it wrong, you'll be given that extra credit. So many people got anywhere from 5 extra points to the couple got 15 extra points. No, but I don't think it, well, let's see, one person got 20 extra points. But your scores did go up for test number 3, and I did, of course, make the adjustment so that the percentage came out correct. So I did that, and it's all correct right now. Your overall grade should be correct. That's shown on Canvas. All right. Any questions? All right. So what I'm going to be doing today is completing confidence intervals. And one of the things I do want to do is not stress so much the PowerPoints. I'm going to show you some PowerPoint slides, but I'm assuming that you're going to be reading these chapters also. But I want to go over the steps of creating confidence intervals, show you the formulas. I'm going to post a PDF document which gives you the overall formulas for creating confidence intervals. I'll show you the calculator steps that are involved. I'll do a sample problem for each one of these things. And then the homework, of course, will give you more practice, additional practice. Now for chapter 8, I do want to show you, before I complete chapter 9, I want to show you something from chapter 8 in the textbook. So let's go to the textbook. All right, and this is chapter 8. This is question number 19. And I believe this is in section 8.2. So section 8.2, the exercises at the end of the chapter, and specifically looking at this particular problem, it's 8.19. All right, so let me read through this problem and I'll show you how to solve this. This is, again, the type of problem I like having on a test. That's why I'm showing it to you, so that you have some idea of what I like to show, because I do like, not all word problems, I do like having word problems because it tells me whether you can apply what you've learned. So anyway, it says here, a manufacturing process is designed to produce bolts with a 0.5-inch diameter. So there is your parameter. Remember, the word parameter means population summary value. In this case, it's a mean, right? But we'll call it a mean. Overall average, we expect a bolt to be, because it's advertised on the packaging, is 1/2 inch in diameter. But of course, there are going to be some variations because of the machine. Now, the variations hopefully are not too much, but there'll be some variation. Now, it says once each day, a random sample of 36 bolts is selected. So we have maybe hundreds of bolts or thousands of bolts created along the assembly line every day, and they randomly select through some maybe systematic random sampling. They select 36 of these bolts, and the bolt diameters are recorded very accurately. Now, it says here if the resulting sample mean, so in other words, they will record the diameter for each of the 36 bolts, and then they will average those 36 diameters. That's the mean, sample mean. So it says here if the sample mean is less than 49 inches or greater than 51 inches, then they shut the process down. In other words, they shut the machine down. They need to adjust the machine. It kind of makes sense, right? If the bolt is if the diameter is too small, or if the diameter is too big, then it's no good, right? It's not going to fit into whatever thing the bolt fits into, right? You've had that, you buy something and the things don't fit, right? So we want to make sure this company wants to make sure that the mean of the diameter of these bolts are not too small or too big. So they shut it down. Now they have a standard deviation for the diameter is 0.02 inches. That is the population standard deviation. All right, that's what they're saying. The population standard deviation is 0.02 inches. So we have a 0.5-inch mean for the population, 0.02-inch standard deviation for the population. What's the probability that the manufacturing line will be shut down unnecessarily? All right, now what does that mean? It means, what's the probability that the mean, the sample mean, is going to be less than 49.49 inches or greater than 0.51 inches. And those are samples that we collect. It's going to be less than 0.49 inches or greater than 0.51 inches. And yet, the true population mean is 0.5 inches. So in other words, it's fine. But that's what they mean by shut down unnecessarily. In other words, the population of bolts, the average is 0.5 inches, but the sample is indicating it is not. All right. So what they're really meaning is that we're going to assume that the population mean is 0.5. That's what it means. All right. Everybody clear on that? And the population standard deviation is 0.02. All right. So let's actually solve this. Write down this information here. The mean is 0.5, standard deviation is 0.2, and we want to find the probability that X bar, now X bar is the sample mean, X bar is less than 0.49 or X bar is greater than 0.5. That's the probability we want to find. We want to find that probability, all right? So let's go now to the calculator. And remember, whenever now we're assuming that the mean of these bolts. Now, all right. Now let's think about this a moment. There's nothing in the problem that talked about the normal distribution. However, we learned, I believe last time, or maybe we will learn. No, I think we learned last week that there's something called the central limit theorem, and the central limit theorem says that if the population is normally distributed, then the sample that we get is also going to be normally distributed for any sample size. But if we don't know that the population is normally distributed, or it's skewed left, skewed right, not normally distributed, then we have to make sure that the mean is large, the sample size is large enough so that the sampling distribution is approximately normal. And large enough in most statistics books is that the sample size is at least 30 or more. In this case, the sample is 36 volts. So it is bigger than 30, and therefore we can assume that the sampling distribution is approximately normal. Now I have to make this really clear to you. This is only true when we're talking about means, all right? Population mean, sample mean. When we're talking about means, the central limit theorem is talking about the sample size being at least 30. When we're talking about proportions, we use a different formula, and which I will go over with you again today, all right? But in this case, what I'm going to do is I'm going to use normal CDF. We want to find a probability, right? So we use normal CDF to find probabilities. All right, and then what we're going to do is we're going to do the first one, that our X bar is less than 0.49. Our probability that the sample mean of 36 volts is less than 0.49. Now, if it's less than, that's a left tail problem, and we're going to use negative 1,000 here. That would work for our lower endpoint. And we're going to use 0.49 for upper endpoint. And the mean is going to be 0.5. Remember, we're assuming that the population mean is that, and the population standard deviation is, what did we say it was? 0.02. We'll scroll down, hit enter. All right, now, if you want, we'll find out what that probability is, or we can put a plus sign and add to it the probability that X bar is greater than 0.51. But I'll hit the enter key just for the fun of it. It doesn't really matter. That's the first probability. But there's two probabilities we have to calculate because it's or, and they're mutually exclusive probabilities, right? The probability that X bar is less than 0.49 is mutually exclusive from the probability that X bar is greater than 0.51. You can't have those two together. They can't happen at the same time. All right, they're different parts of the number line. So we're going to put a plus sign here. So we have our first probability, and then we repeat the whole process again here with normal CDF. This time we want X bar to be greater than 0.51. That's a right tail problem. So I'm going to type in 0.51 lower limit, positive 1,000, the upper limit, and everything else is the same. And that is the overall answer, 0.617. So that's the probability that the manufacturing process will be shut down unnecessarily. All right. There's a 61.7% chance of it happening, all right, which is pretty high. Now, I noticed something that I did wrong in this here, because that seemed kind of high, doesn't it? I purposely did this incorrectly because I'm looking at the answer, I'm saying, that's a really bad manufacturing process. If there's a 61.7% chance every day that it could be shut down, there's something wrong with this process. Now, can somebody tell me what I did wrong when I entered these two normal CDFs? There's something I did wrong. Look at the first part. First one, hit enter again. The reason I like doing this, I like showing the wrong answers, is because many students will put something like this down and then move on, and you know, if it's multiple choice, they'll see the answer in the answer key, they think they got it right, but this is not right. What is it about these four numbers here that one of these four numbers is incorrect? Which one is it? I'm going to scroll over, and I'm going to tell you it's the fourth number here, 0.02. Is incorrect. What I just came up with here is the probability that X is less than 0.49. In other words, what's the probability that if we selected one bolt off the assembly line at random? What's the probability? Well, this is the probability here. But I'm not saying the probability of one bolt. I'm saying what's the probability that the mean of 36 bolts is less than 0.49. That's a different probability. So what we have to use, this is the most important thing you have to remember when you do this problem, you need to write this down, is that you need to use the standard deviation of the sampling distribution, in this case of sample means. And remember, the standard deviation of the sampling distribution is the population standard deviation divided by the square root of the sample size. And that's what I forgot to do here. So I'm going to insert it. You can actually use second, insert here. Right? And I'm going to put divide by the square root, there it is, square root of 36. I could have put divided by 6 because I know the square root of 36 is 6, but let's just let the calculator do all the work. Now I'm going to hit enter again. Wow, look at how small, much smaller that probability is. That makes more sense, right? Makes more sense that it's highly unlikely that this process is going to be shut down. Now I'm going to add to it. I have to correct the second one too. So I'm going to hit the plus key. Now I have to go back to the second one that we did. It was this one up here, and make the same correction to the standard deviation. So I'm going to go here to right here, and I'm going to do insert. Second, delete is the insert one there, and I'm going to divide by square roots of 36. Hit enter. Now I'm going to get the true answer. It's 0.004. That's better. There's a 0.4% chance that the process on any given day, the process will be shut down unnecessarily. That's good, right? 0.4% or 0.004 probability. So you have to remember that when we're doing inference, we're using samples. And that means with probabilities, we're using the sampling distribution. All right. And the mean and the standard now the mean of the sampling distribution is the same as the population mean. The two are equal, but it's the standard deviation that's different. The standard deviation of the sampling distribution is the population standard deviation divided by the square root of the sample size. And this is when we're talking about means. All right. We're talking about variables that are measured, and we're taking the mean of these variables. Right? With proportions, it's the same idea, but we use a different standard deviation formula for that. All right, so I wanted to show you this, both the wrong way of doing it and the correct way of doing it, so that you don't fall into the trap of doing it the wrong way. Because if you do, and it's multiple choice, I can guarantee you the answer is going to be in the answer key, the wrong answer. And you will select it, and you think you got it right, and you didn't. So just be careful. You have to make sure that you don't make that mistake. All right. Any questions about that? All right. So that to me was a good one to do. Then in that's chapter 8, and this will be obviously true in chapter 9 too. We're using the sampling distribution. I want to show you in section the next section in your book. Another example. Let's go back to the book. And it's in section 8.3, exercises at the end. There's another example there I'm going to show you. And the exercise is number 30, 8.30. Let's look at it, 8.30. Let's read through it. Suppose that a candidate for public office is favored by 48% of all registered voters in his district. So this is a proportion question, right? 48% means we're counting the number of voters who like this candidate versus another candidate or other candidates, and we're dividing that by the population, number of people in the population. We're saying 48% or 0.48. A polling organization will take a random sample of 500 voters. There's your sample size. And we'll use p hat, the sample proportion, to estimate p. What is the approximate probability that p hat, that means any sample size What size? 500. What's the probability that the sampling proportion of size 500 will be greater than 0.5, causing the polling organization to incorrectly predict the result of the upcoming election? Well, let's think about that. Okay. Candidate is favored by 48%. Now, typically this is unknown, but we're assuming that it's known, all right, for some strange reason, maybe just to illustrate how to do this arithmetic here. But we're also doing a sample, and we want to know if we took a sample of 500 voters, what's the probability that the sample proportion of people who like this candidate will be greater than 0.5? If it's greater than 0.5, the sample's saying the person's going to win, right? Over 50% of the voters like that candidate and will vote for that person wins. But that person will win incorrectly because the true population proportion is what? 0.48. All right, so so 0.48 is P, the true population proportion. And we want to know what's the probability that P hat will be greater than 0.5, given the true population proportion is 0.48. We know our sample size is 500. So let's now go back to our calculator and do this problem. Find that probability. I'm going to clear all this out because now we're doing proportions. Now, once again, it's a probability. And now, can somebody tell me, before we use normal CDF, how do we determine if the sampling distribution, right, is approximately normal? Does anybody remember how to do that? Because you do need to know this for not only this next test, but for the final exam. It is tested by the department. The department wants to know, make sure that you know this. One of the requirements. So what is it that we want to make sure to assume that the sampling distribution of sample proportions is approximately normal? We have to do some calculation. Anybody remember what that is? And it's not, I have to tell you, it's not that the sample size is greater than 30. When you're dealing with proportions, that is not, we don't use that. We use another rule. Anybody remember what that rule is or read about it, maybe? Okay, so you don't remember, all right. It doesn't surprise me because we only talked about it last time. We take N times P, the sample size times P, the population proportion, and then we take N, the sample size, times 1 minus P. We do these two multiplications, and in both cases, the resulting product has to be at least 10. So NP, when you multiply N times P, it has to be at least 10, and N times 1 minus P also has to be at least 10. If one of them is less than 10, then we cannot use the normal approximation. That's the rule. That's sort of like the central limit theorem for proportions. It's not called that, but that's the rule that we use. And in the book, they say they call it the large sample proportions. Okay, it doesn't matter, but that's the rule that we use. So we know that 500 is N, and we know that 0.4, what was that, 0.47 or 0.48? What did I say before for the population proportion? What did the problem say?
0.48.
0.48. So if you take 0.48 and multiply it by 500, right? 0.48 times 500, what do you get? You can use your calculator. Tell me what number you get.
240.
240. That's well above 10. All right, now 1 minus P is 1 minus 0.48 or 0.52. What's 500 times 0.52?
260.
Yeah, and that's well above 10 too. So we're good. You have to always do that. We have to make sure that those two products are at least 10. If they are, we can use the normal CDF to do this problem. If it's not, we have to use some other method. We cannot use normal CDF, all right? So let's go to normal CDF. We did that calculation. Now, we want to know the probability that P hat, that is the sample proportion for 500 voters. So if we take a sample and of 500 voters, we want to know the probability that we get at least 50% of them. That means 250 or over, or it's over 250. You want to make sure that over half of them are going to be saying they like that candidate. All right. So a greater than problem, well, again, is right tail. So we're going to use 0.5 for the lower part of the interval we're looking at, and we'll use positive 1,000. That'll work for the upper. The mean is 0.48. Remember, that's the mean. Now, what are we going to use for the standard deviation? We have to use the sampling distribution, the standard deviation of the sampling distribution of sample proportions. Anybody know what the formula is for that? It's in your book, but hopefully you've read through it.
Repeat the question.
The sample standard deviation of the sampling distribution of sample proportions. Anybody know the formula for that? All right. So I'm not going to wait too much longer. So it's the square root of P, which in this case is 0.48. If we know the population proportion, we use it. So it's 0.48 times 1 minus 0.48. Now we know it's 0.52, but I'm just going to type it in that way. All right. Those of you who don't like doing arithmetic, just type it in. And then so we multiply P times 1 minus P, and we divide by the sample size, which is 500. This is all inside that square root, all of it. Close the parentheses. That's the standard deviation of the sampling distribution, all right? Of sample proportions. That's the formula for proportions. Scroll down, hit enter, and there's your answer. That's the probability. 0.185 if we round to 3 decimal places, or 18.5% chance, okay, that a sample of size 500 will have at least 50% of the voters liking that candidate. Incorrectly, by the way, incorrectly, because the true population mean is 0.5. Excuse me, the true population proportion is 0.5. Or is it? I'm sorry, 0.48. All right, let me say that again. This 0.185 is the probability that if we chose a random sample of 500 voters, this is the probability that that sample of 500 voters would have a sample proportion of at least 0.5, given that the true population proportion is 0.48. That's why we put 0.48 for the mean here, because that is the true population proportion. Once again, the mean for proportions, the mean of the sampling distribution for sample proportions is equal to the population proportion. The standard deviation of the sampling distribution of sample proportions is equal to the square root of the population proportion times 1 minus the population proportion divided by the sample size, the square root of all of them. All right? This is what you need to know. There's not a whole lot of formulas. And by the way, it's open book, so you don't have to memorize it, but you have to know it. You have to know where it is, and you have to know how to apply it.
Professor,
Yes?
you said that the mean of the sample is the proportion of the population?
No, not the mean of the sample. The mean of the sampling distribution of sample proportions is equal to the population proportion. In other words, if you listed all possible samples of 500, maybe there's billions or trillions of them, and for each one of them, or for each of those samples of 500 people, you ask them, which candidate do you like? They're going to say either candidate A, or they're going to not say candidate A. All right. So, and then you just count and then you have a sample proportion of people for each of those samples of 500 who like that candidate, right? You just add up all the people who like that candidate and divide by 500 people, by 500, and you get your what? You get your sample proportion. So if you did that for all billions and billions of these samples, and then you averaged all those proportions, sample proportions up, they will mathematically be equal to the population proportion. Just mathematically, it works out. So that's always true for sampling distributions. The mean of the sampling distribution is always equal to the population parameter, period. Whether it's the population mean or the population proportion, whatever we're looking at. The standard deviation is different. For a sampling distribution of sample proportions, the standard deviation is the square root formula that I just showed you. If we are looking at the sampling distribution of sample means, which was the problem we did in the previous section, then we use what? Population standard deviation divided by the square root of the sample size. All right? So that's 4 pieces of information that you need to know. And I'm testing you on it. Guaranteed quizzes, homework, tests. I'm testing you on all that. You have to know that. All right? It's very important to know that. There's a lot of other stuff that's in these chapters. That's the most important part right there. And that's what's tested on the final exam also. All right? You just have to know that. Now, you don't have to memorize it, but you have to know it. That's why I always say open book is dangerous, because many students don't take the time to learn. They think I can just look it up. No, not with math. This is not history. This is not some other subject where you could just look up something. You have to know it. You have to know how it works. All right? So it's not just being able to look it up. You have to also know how it works and know how to use the calculator to come up with your answer too. And that's why I'm showing you all this, so that you know how to do the problem. It's the key. Key to get a good grade in this class is that. All right. All right. All right. Let's now go to chapter 9. We'll finish this. We'll go to chapter 9. And the first thing I want to share with you is a formula PDF. Now I want to explain what the PDF is. I want to go over it with you. Now that you know about the mean and standard deviation of sampling distributions, that was one of the reasons I also wanted to go over that problem, because I wanted to review that with you. I want to talk about now confidence intervals. All right. So I'm going to use this PDF as a teaching tool, and then if we have time, I'll go through the PowerPoint, but the PowerPoints aren't as important for this class, this particular class, as going over what I'm going to show you now, and also some sample problems, all right, so that you understand exactly how to create a confidence interval. Now, what is a confidence interval? It is a way of estimating the true population parameter. Remember, the word parameter is the true population mean or true population proportion, depending on which one we're looking at, all right? The letter C represents confidence percentage, confidence level, all right? When I say C% confidence interval, I'm talking about a percent confidence level. Now, what does that mean? Once again, if you list all the possible samples of a certain size, and for all those samples, we either are going to be calculating a sample mean or sample proportion, depending on, again, which situation we're in. All right, if we're measuring something, it'll be a sample mean. If we're counting people for a poll or something like that, it's a sample proportion. All right, you're going to, for a certain sample size, you're going to have all possible samples of that size listed. Okay, and you're going to calculate your sample statistic. So the sample statistic is called a point estimate. It is one number that estimates the true population parameters. So if I say X bar is equal to 50, the sample mean is equal to 50, whatever 50 is representing. All right, that's the sample mean. Mu is the population mean. We're using that sample mean to estimate the population mean. So the sample mean is called a point estimate. Same thing with proportion. When we do a sample proportion, that is a point estimate of the population proportion, all right? And that's for a particular sample. Now, we have a bunch of point estimates for all possible samples of a certain sample size, all right? We take the mean of all those sample means, if it's a mean, if they're sample means, if we take the mean of all the sample means, that mean is the mean of the sampling distribution of sample means, and it's going to be equal to the population mean. Right? Absolutely certain. Same thing with proportions. All right, if we find sample proportions for all possible samples of a certain size and we average them, the mean of the sampling distribution of sample proportions is going to be equal to the population proportion. And then we have the standard deviation formulas that I just went over. All right, that's what you need to know. Now, a confidence interval is another way of estimating the population parameter because of what's called sampling variability, right? Different samples of a certain size are going to have different sample statistics. So if everybody in this class took a sample of 100 Rowan students and asked measured all 100 Rowan students, measured their heights and then averaged their heights, all of you would get different sample means because you would all have different groups of 100 students, all right? That's called sampling variability. So instead of using it, so when you come up with your own sample, it's one of many possible samples. That sample mean may be close to the population mean, may be further away from the population mean than another sample mean, all right? So what's a better way of doing it? Come up with a range of possible values that estimate your population mean or population proportion. And a way to do it is use what's called a margin of error. You calculate what's called a margin of error, and then you add and subtract that from your sample mean or sample proportion, right? And you get your interval. And here's the general formula for estimating a population parameter. Now I'm using this these symbols here, less than and greater than, all right? So that you can understand that what we're saying is that the population parameter is somewhere it's hopefully somewhere in between the point estimate plus the margin of error and the point estimate minus the margin of error, somewhere in between those two numbers with a certain degree of confidence. Now, what does this degree of confidence mean? If I say 95% confident that the true population parameter is in between two numbers, what do I mean by that? What I mean is that if I listed all possible samples of size of a certain size, and I created a confidence interval for each one of those, because all of them will have different confidence intervals because they all have different sample statistics. Okay? Once I've calculated all their confidence intervals, I'm hoping that around 95% of them contain the true population mean. In other words, either your interval is going to contain the mean, or the mean's going to be outside that interval. So when I say 95% confidence, I'm not saying there's a 95% probability that your interval contains the population mean. I'm not saying that. I'm saying I'm 95% confident that out of all the possible all the possible confidence intervals that you could create from all the possible sample means, that this one that you actually have, this particular sample that you actually have, this confidence interval that you've actually constructed does contain is one of those 95% that does contain the true population mean. That's what we mean by it, all right? We expect 95% of all possible samples to contain the true population mean or proportion. All right, so that's what we mean by level of confidence, and the level of confidence will determine your margin of error. It'll be one of the determining factors. Okay, the other thing is going to be one of the other things is going to be your standard deviation, and another thing is going to be your sample size. All right, we'll get into that in a minute. All right, now the margin of error, when it's constructed this way, the way that it talks about in the book in parts 9.1, 9. All the sections of the first three sections of chapter 9, not the later ones, but the first three sections, 1, 2, and 3, they all assume that the margin of error is calculated by finding what's called a critical value and multiplying it by the standard error. Now, what is the standard error? It is the standard deviation of the sampling distribution with a possible estimate, an estimate for what? For some of the things that are in that standard error, which I'll talk to you in a minute about. So it's these two things, that's it. A number called the critical value and a number called the standard error. Now the critical value is determined by what? By using inverse normal. Inverse normal will give you the critical value. So it's that value of z which gives you that area to the left, all right? And again, I'll show you what I mean in a minute. Standard error is that standard deviation of the sampling distribution, those things that we were just talking about. Now, if we're estimating a population parameter, which is the population proportion P, then this is the formula, this is the confidence interval. The left endpoint is going to be P hat, your sample mean, the sample proportion for that sample that you have, minus, and this whole thing here, this z times the square root is your margin of error. Right? Now, what is z? That's the critical value. What's the square root? That is the standard deviation of the sample of the sampling distribution of sample proportions. But notice here, instead of putting p inside here, we put p hat. We replace the p inside the square root formula of p hat. Why? Because we don't know p. We're estimating it. So the next best thing is to put in your actual sample proportion for that sample that you have. Just plug it in for p. You're estimating it in here. And that's why it's called a standard error, because it is an estimated standard deviation, this whole formula here. So it's p hat times 1 minus p hat divided by n. That's your standard error. That square root is your standard error. And your critical value is z. And again, I'll show you how to do it. We'll do an example with this in a minute. Now, on the right end of the interval is just plus this margin of error. All right, so it's p hat plus margin of error on the right side, p hat minus the margin of error on the left side, and you have your confidence interval. All right. Again, I'll be posting this so you'll have it. Now, if you are estimating the population mean through a confidence interval, and then there's one more piece of information you need to know in this case, just in this case here for population means. If you know the population standard deviation, sigma, if you know it, then this is the confidence interval. And once again, the margin of error is going to be the critical value times the standard error. What is the critical value? Again, z. All right, and then the standard error is this population standard deviation divided by the square root of the sample size. So this product of the critical value z times the standard error sigma divided by the square root of n. This whole thing is your margin of error, and you're adding it, subtracting it to what? Your sample mean, x bar, your sample mean. Okay. Now, in many cases, I would say most cases, we don't know the what? We don't know the population standard deviation. So if it is unknown, then we have to use something different. So if sigma is unknown, then we're going to replace the sigma in the standard error form, standard deviation formula here, sigma divided by square root of n. We're going to replace it with the sigma with s. That is called the sample standard deviation. All right, that's s, sample standard deviation. And there's one more thing that we replace in this margin of error formula. We replace the z with what's called a t. This is a different probability distribution that looks like the normal, but it's a little bit different. It has certain properties, which I'll talk about in a couple minutes. And I'll show you how to access it with your calculator. All right. So, just give me a second. Let me move this thing out of the way here. Fortunately, Zoom has all these little boxes. All right, here we go. So X bar is the point estimate, the sample mean. T is the critical value. Again, I'll show you how to access it with your calculator. And S divided by the square root of n is your standard error. So now, this is when sigma is unknown. If it's not given in the problem, if the population standard deviation is not given in the problem, if the sample standard deviation is, we use S in the standard error formula, and we use T critical value. All right, so this is basically the formulas that you need to know to construct confidence intervals. And that's it. That's what you need to know for this course right here in this one page. All right, so what we're going to do now is, I think the best thing to do, instead of going into the PowerPoint, because we're running low on time, I'm going to show you exactly how to do this using your calculator. All right, so I'm going to, now, one thing I do want to show to you, before I do that, I want to go back to the ebook. Now I want to go to chapter 9. I will be in chapter 9. And I want to go to 9.3. Now 9.3 is that section which we did not cover yet, which is the section on confidence intervals for population means. Now I'll post the PowerPoint and all of that, but I do want to bring out something to you, the T distribution. I'm going to click like that. And let's talk about that a little bit. Now, the T distribution is very similar to the standard normal because it has a mean of 0, just like the standard normal has a mean of 0. However, this T distribution's standard deviation is not 1, because the standard normal has a standard deviation of 1, right? A mean of 0, standard deviation of 1. The T distribution has a standard deviation bigger than 1. All right, not a big deal, but that's something you should know. So as the T distribution it's bell-shaped, it looks like the normal, has a mean of 0, but its standard deviation is a little bit bigger. That means it's a little more spread out than the standard normal looks. And it has a property called degrees of freedom. All right, degrees of freedom. Now, what is the degrees of freedom? I can give you a technical definition, but it's not really going to be helpful to you. What it is, in this particular case, it is the sample size minus 1. So, for example, if we took a sample of 100 people to be in a study of, people that we're measuring their heights, and we want to see what their heights are, average heights. Then, if n is 100, then the degrees of freedom is 100 minus 1, or 99. All right. So with a normal distribution, what do we need to know for any normal distribution? The mean and the standard deviation for that normal distribution. What do we need to know for a T distribution? Degrees of freedom. The degrees of freedom determines what T curve we're looking at, and that's it. So just one parameter that's used for the T distribution, and it's called degrees of freedom. And it's just simply the sample size minus 1. All right, and that's it. Now you can read more about the T distribution here. I would recommend reading this section and knowing a little bit more about it. It shows you how it works, and it shows that if the degrees of freedom gets large enough, that the T curve looks just like the standard normal curve. All right, fine. But let's look at the T curve. It looks like, in this case, the standard normal curve. And we're going to talk about it in the same way we talk about a standard normal curve. Here's the middle of it, which is 0. And then we have numbers greater than that, which will be positive. These are T values. And we have negative T values. All right, you see all of that? All right. So that's your T. And then on the next page, let's go to the next page here. Here's the formula for creating a T score. Remember, we had our Z scores. Here's the Z score formula for sample means. It's the sample mean minus the population mean divided by the standard error, divided by the standard deviation of the sampling distribution, right? This thing is the z-score. This is how you convert a sample mean to a z. This is how you convert a sample mean to a t. Notice it looks almost like the same formula up above here, with the exception that you're replacing sigma with s. So you take your sample mean, subtract the population mean, and then the denominator here is the standard error, s, the sample mean, divided by the square root of n. And the t distribution has n minus 1 degrees of freedom. All right? Now, let's actually do a confidence interval question with this. Let's just do 9.3 first, and then we'll go back to 9.2, and I'll show you an example of that also. All right? So let's go to the end of this section here. 9.3, let's look at some exercises. All right. Now, let's show you how to use your calculator to find a probabilities using the t. All right. So let's just do an example. Suppose we want to know, it says what percentage of the time will the value fall in indicated region. That's the same thing as saying what's the probability that t is, the t value is going to be between two values and with these number of degrees of freedom. So let's just do the first one here. All the others pretty much the same. All these other ones that are listed here. So let's find the probability that t is between negative 1.81 and positive 1.81 with 10 degrees of freedom. So let's go to the calculator, show you how to use your calculator for this. Now this is going to be true for all of your calculators, 83 and 84 calculators. One of the options that's listed down here is T-CDF. So instead of using normal CDF, if it is a T, we're going to use T-CDF. Hit enter. Now those with the 83 calculator, again, you won't see this screen. You'll see T-CDF with an open parentheses. Once again, if you're trying to find probabilities, you're going to have a lower part, an upper part, upper limit, and notice here, instead of having mean and standard deviation, it has DF. We put in the degrees of freedom. All right. Now, can somebody tell me, was it negative 1.81? Was that it? I believe in positive 1.81. I think that's what it was.
Yeah, it was.
Yes. So remember, don't use the minus sign, use the negative sign down here. Negative 1.81. So we're going to find the probability that t is in between negative 1.81 and positive 1.81. And it's with 10 degrees of freedom. Now, by the way, if the degrees of freedom is 10, can somebody tell me what the sample size is? Remember, degrees of freedom is equal to the sample size minus 1. So if the degrees of freedom is 10, what's the sample size?
11.
11, right? So sample size is always one more than the degrees of freedom. In this case, if you take any more advanced statistics courses, degrees of freedom will change depending on the circumstances. But this is the only thing that we need to know about the t, is n minus 1 is the degrees of freedom. So we'll go down, hit enter. This is what you'll enter as 83 with your 83 calculator. Hit enter again, and there's your probability. So it's almost like normal CDF, with the exception that we're going to use degrees of freedom only, and not the mean and standard deviation when we calculate T-CDF. Now, if we want to do the reverse, if we want to find the T given the area, those of you who have the 83 calculator, or excuse me, 84 calculator has this function called inverse T. Unfortunately, those of you with the 83 calculator don't have this. So you have to learn how to find this using Microsoft Excel. I'll show you in a second how to do that, all right? Or actually, you know what might be better? No, I'll show you in a second. I think it'd be better if I just showed you while I'm recording. So we use inverse T. And inverse T looks like inverse normal. Pretty much the same thing, except that once again, Instead of the mean and standard deviation, you have degrees of freedom. The area, once again, will be the area to the left. So for example, if we wanted to know what is the t value, if the area to the left is 0.95, area to the left, and we know that it's for a sample of size 50. So what am I going to put in for degrees of freedom if the sample is of size 50?
49.
49.
Wow.
Scroll down, hit enter. And this is the t value where the area to the left of it is 0.95. So you draw a t curve, looks like a normal curve, and then to the right of 0, which is the mean, you'll show 1.676, and then you just color in the area to the left. That's 95%. The area to the left of that is going to be the area under the curve to the left of 1.7676. All right. So pretty much the same way you use normal, inverse normal, except you're going to put degrees of freedom in there instead of the mean and standard deviation. It's exactly the same thing. Now, for those who have the 83 calculator, see what I have to do here. Just give me a second. Let me open up Microsoft Excel. And now there is, if you want to, you can go online, and there is, you can do Google 83 calculators and inverse T. Let's type in INT, INVT, and 83, TI-83 calculator, and it'll show you step by step how to program your calculator for the inverse T. All right. Now, typically, if we were doing this in class, I have a power connection, and I have it on my calculators. I would just have you come up, and I would just put the program right onto your calculator. But obviously, we can't do that. So I'll show you how to do this. If you don't want to go online and learn how to program it, it will take you about a half an hour to listen to the video and program it. You can just use Microsoft Excel for this. All right. So I'll show you how to do it. So just pick any cell in Microsoft Excel, hit the equal key, and then you're going
to see your screen.
Oh, I'm sorry, you're not seeing it. Yeah, sorry. Thank you for letting me know that. All right, so let's go to Excel. Hold on a minute. Okay, second here. Let me open it up. All right, where are you? Huh. I don't know why it's not opening up for me. All right, hold on a minute. All right. Try it again. There it is. So fickle. All right, anyway, go to any cell. Inside the cell, hit the equal sign, and then start typing in start typing in T. Put the letter T first, T distribution, and then you'll see a list. Now, if you scroll down, you'll see T.INV. That's the inverse T. So just double click that. It'll open up a set of parentheses. And then the probability is the area to the left. You put it in as a decimal. So again, put 0.95 in here, and then put comma, and put degrees of freedom, like we just did a minute ago, right? 49 degrees of freedom. Then close parentheses. You can see how easy this is. And then hit enter, and there's your answer. See how easy it is? So you don't want to go through all the trouble of programming your 83 calculator. Use Microsoft Excel and just follow the steps I just showed you. Now, all right, everybody see that? All right, that's it. That's all you do. And as long as you have Microsoft Excel on your computer. All right, so let's actually spend a couple minutes I might end up running about 5 minutes over today, so if you can stay, good. If not, it'll be recorded, so you can go back later and watch, all right? But there's so much material here. Again, I wish this was a 4-credit course. We'd have extra time to do this, but it's so squeezed. It's pretty unfortunate for that. But anyway, let's go back to the book. All right. And what I want to do now is go to a particular, go to 38. I want to show you a couple things here. Here's number 38. Now, this is another way of showing a confidence interval. Instead of saying mu is less than 115.6 and greater than 114.4, they'll put it as parentheses with a comma in between, but it means the same thing. It means we're estimating mu, that mu is being estimated between these two numbers here. And the same thing over here. So suppose there were two people, and they were, or maybe this is the same person. This is the same person, all right? Two intervals are created, two confidence intervals are created, all right? And it's measuring what? The mean resonance frequency for all tennis rackets of a certain type. All right, whatever. It doesn't matter what it is. It says, number one, what is the value of the sample mean resonance frequency? Now, we're assuming this is the same sample. The same sample mean is used to create these two intervals. Now, you might say, why are they different? Well, there might be a reason for that. And the reason might be because they are different levels of confidence. Different levels of confidence. So we have to determine how to calculate what we mean by that. All right. So number one, if you see, if I give you a confidence interval, it has a left end point and a right end point, how do we determine the mean? Well, remember the formula. Let's go back to that PDF that I have right here. Scroll back up. Remember that the confidence interval is being created by taking our point estimate, in this case, the sample mean, and adding and subtracting the margin of error. So we're adding and subtracting the same number, which is called the margin of error. Okay. So that means the mean is in the center of the two endpoints. That's not what it means. It means that. It means it's at the center of the two endpoints. Okay. So how do you find it? Well, one way of finding it is simply taking the average of these two numbers. Because the mean is in the center, if you add these two numbers up and divide by 2, you will find the mean. Or another way of doing it is subtracting these two and dividing by 2. Right? Or no, let me rephrase that. To find the mean, we would subtract these two, divide by 2, and add that to the left endpoint. Now, as I said, wait, you're going too fast, Professor Barish. What do you mean? Well, remember the confidence intervals being created by taking a number, the mean, the sample mean, and adding to it the margin of error, and also subtracting from it the margin of error. And when we do that, that means the difference between the left endpoint and the right endpoint must be 2 times the margin of error, right? It must be twice the length of the margin of error because we're adding it and subtracting it. So, number one, if we want to find the margin of error, that's the first thing, we subtract these two numbers and divide by 2, and we'll get our margin of error. And then we can just simply add that to the left endpoint, and we would get our mean, because that's how we got the left endpoint, is we subtracted the margin of error from the mean. Okay, so let me say that again. To find the margin of error, you subtract these two numbers and divide by 2. And then if you add that to the left endpoint, the margin of error, you would get your sample mean. So, and it's all, and that number, the sample mean, will be halfway in between these two numbers. Can anybody tell me what the sample mean is in this case here?
115.
115, yeah. And once you figure this out, it's pretty easy that this is also the sample mean, right? 115, right? right? If you subtract these two numbers, you get 1.8 and divide by 2 is 0.9. 114.1 plus 0.9 is 115. So these two intervals were created from the same sample with the same sample mean of 115. But they have different margins of errors. The margin of error of the first one is 0.6. The margin of error of the second one is 0.8. So this second one has a larger margin of error. Now, if it's from the same sample, that means the sample size is the same and the standard deviation is the same. What's different? The level of confidence. Now, remember the formula. Let's go back. Go back to the formula. The level of confidence, okay, determines what? The critical value. And the critical value is being multiplied times the standard error. So the bigger the critical value is, the bigger the margin of error. Everybody clear on that? The bigger, if the standard error is the same, the standard error in this case would be the standard deviation divided by the square root of the sample size. So that's the same. The only difference between those two confidence intervals is the critical value. And the bigger the critical value, the bigger the margin of error. And the bigger the margin of error, the wider the confidence interval. Okay? So let's go back to that example in the book. This is very important what I'm trying to show you here. We have two confidence intervals created from the same sample. And which one is wider? The second one's wider. Now, how do you create a wider confidence interval? Through a bigger margin of error. And a bigger margin of error in this case is due to what? A bigger critical value. Now, how do we get a bigger critical value? Let's go to our calculator. Assuming here, let's assume that we know the population standard deviation. We assume we know it, and the critical value will be a z. All right. All right, so we're assuming we know the population standard deviation. So find the critical value. We go to inverse normal. And suppose it's a 90% confidence interval.
I can't. We can't see your screen.
Yeah, once again, I'm sorry. Yep. So let me hold on one second. Sorry about that. Now you can see. All right, once again, let me just go back out. Again, we go to inverse normal. We're assuming, again, we're using a z for a critical value. Let's say we have a 90% confidence interval. I think I went over this last time. That means the middle area of the normal curve is 90%. All right, middle area is 90%. So that means that the area to the left of the critical value is going to be the area in the middle plus the left tail. So if it's a 90% confidence interval, that means there's 10% left, 5% on the left tail, 5% on the right tail. That means the area to the left is 95%. So for a 90% confidence interval, the area to the left is 0.95. Right? And the critical value is always going to be a z. So we leave the mean standard deviation as 1. And that is our critical value. That's it. Now, what if we wanted to know, have a 99% confidence interval? All right. Well, let's find the critical value for that. Scroll down, enter. Now, a 99% confidence interval means the area in the middle of the curve is 90.99. That means there's 1% left, half of a 1% on one side, half of 1% on the other side. That means the area to the left is 0.995 for a 99% confidence interval. And notice the critical value. It's larger, isn't it? Now remember, a larger critical value means what? Larger margin of error. And a larger margin of error means what? Wider confidence interval. Everybody clear on that? So as we increase the level of confidence, the interval becomes wider. Okay, so let's go back to that problem. You need to watch this a few times, right? This what I'm talking about right now. It's extremely important. I'm telling you, very important. If you get this concept right, you'll be in great shape. Which interval is wider? The second one, right? How do we know it's wider? Just subtract these two numbers. It's 1.8. This one's 1.2. The wider confidence interval must be mean what? If we keep everything else constant, the sample size, and we keep the standard deviation constant, the only thing that can be different between these two intervals is the level of confidence. And since this one, the second one is wider, it must have the higher level of confidence. So if one of them, in this case, now I said 90%, 95%, but it doesn't matter. Whichever one has the higher level of confidence will be the wider interval. So that means the first interval must be the 90% one, and the second one must be the 99% one. Okay? Now, what if we keep the level of confidence the same, but we change what? So we have two different samples from the same population, right? And what if the sample size is different, but everything else is the same? The standard deviation is the same, the level of confidence is the same, but the sample size has changed. Let's go back to the formula. Okay, critical value. It doesn't matter which critical value, excuse me, it doesn't matter which standard error we look at, whether it's for a mean or for a proportion. They're all divided by n, which means that as the sample size increases, the standard error decreases. And it's true for all three of these that you're looking at, all three of them. As the sample size n increases, the standard error decreases. And if the standard error decreases and everything else is the same, the margin of error decreases. And if the margin of error decreases, the width of the interval becomes more narrow, not wider, more narrow. So as you increase your sample size, you end up with a more narrow confidence interval. And we'll go back to here, back to the screen. Look at the example here. Again, you should read through this so that you're sure about it. They're comparing two different samples. Now these are two samples, different sample sizes. You have to determine which one is wider and which one is narrower. The one that is narrower has the larger sample size. Okay? And that's the reasoning they use. And this is the type of thing that I do test you on the test number 3 and also on the final exam. And that's why I'm going over it. All right. Now, one other thing, a couple more things I want to show you. I know I'm running over, but again, if you can stay, fine. If you have to leave, this recording will continue. And I just feel bad that I wish we had more time, but I'm just continuing with this. If we go to, again, 9.3, and we go to problem number 42, scroll down here. And I just want to show you in general how to do this. Here is an actual sample. All right, an actual sample. They give you the numbers. These are individual numbers for 24 students at Cornell. All right. Now, there's no information in this problem about sample standard deviation or population standard deviation. However, if you put all these numbers into your calculator and go to one variable statistics, you will get the sample mean, X bar, and S, the sample standard deviation. All right, so that's how you would have to do a problem like this. You'd have to do that first to find the sample mean and standard deviation. And then if it asked to construct a 90% confidence interval, then you would use, let's go back to that PDF. You would use this formula right here because sigma is unknown. You're not even giving it to you, so you don't know what it is. But you are given enough information to get S, the sample standard deviation, and you'll get X bar by, again, putting it into your calculator. The only other thing that you need to calculate is the critical value t. Now, if it is a 90% confidence interval, and they give you the sample size, let's go back to the calculator. Actually, let's go back to the problem. N is 24, so if N is 24 students here, what is the degrees of freedom?
23.
23, so remember that. If N is 24, degrees of freedom is 23, right? And we know that 90% is your confidence interval, all right? So how do you find the critical value? Okay, go to your calculator. This time we would use inverse t. And again, if you don't have this on your calculator, you go to Excel. It'll give you this, like I showed you a minute ago. Now, if it's a 90% confidence interval, that means the area to the left has to be 90% in the middle plus 5% to the left, right? Like I said before, 0.95. Degrees of freedom is 23. And then you scroll down, hit enter. And there is your critical value. Now, by the way, if you wrote down what S is, you can simply hit the multiplication key here. I'm just showing you a little trick here. If you hit the multiplication key and you type in your standard error, let's say I'm just assuming it's 12. I'm just making it up. 12, and then you divide by the square root of the sample size, which is 24. Remember, put 24 here, not 23, and hit enter. That's your margin of error. How about that? So in one step, you do the critical value, you multiply it by S and divide by the square root of N, and there is your margin of error. And then you simply add and subtract that from the sample mean, and you get your confidence interval. All right? Any questions about that? And then one other, now, if you're in section 9.2 and you're creating a confidence interval, remember that once you find the critical value, now the critical value for a proportion is always going to be Z, never T. So T is always for means when you don't know the population standard deviation. And so for proportions, we always use Z for the critical value. And remember, we use square root formula for the standard error. And remember, because we are estimating P, we have to use P hat times 1 minus P hat divided by N inside the square root as our standard error. Once we multiply our critical value times our standard error, again, we get our margin of error. All right? Now, the last thing I want to show you, or maybe I'll just do it next time. Yeah, let's do it for the first 10 minutes next time. I want to show you what's called a minimum sample size problem, which always shows up on tests. And I'll show you an example for a proportion and for a mean. All right, so it's called minimum sample size. And it's something that people determine before they actually run the study, or experiment, whatever they're doing. All right, so I'll show you how to do that next time for both means and proportions. And then we will start what's called hypothesis testing next time, the next chapter 10. And of course, we will also have a quiz that will begin, that will cover chapters 8 and 9. All right. So any questions about anything we covered today? It's a lot. You really have to do a lot of work on your own here, because again, the math department gives you a lot to do at the end of the semester. And I've talked to them about it, but they assume all students are going to work really hard and read the book and do their homework, all of that. So make sure you do read the book and look over the slides and all of that. There's only so much time I have to show you everything. All right, if there's nothing else, I will exit out now, and it'll be a longer video this time, but hopefully it'll be useful to you. So I'll stop the recording. There's no other questions.